All right, welcome back. Chapter 5. We're better than halfway done. So, well, we are halfway done. This will start the second half of the course. So tonight we're going to talk about spatial data as it refers to map projections, coordinate systems. We're going to talk a little bit about how to get data from the census and get your maps working correctly. So let's just jump right into coordinate systems. So in rough terms, coordinate system measures the location on the surface of the Earth based on the angle of rotation from the point at the center of the Earth. So we refer to this as latitude and longitude. It's pretty much standard worldwide, and you can measure any point on the globe fairly accurately using this coordinate system. So it's divided into longitude, which are the lines that go up and over the Earth. So you can a little mnemonic device for remembering that. Longitude goes over, O for over. Latitude refers to the lines that go around the Earth. So latitude with an A, O for around. So the equator is a line of latitude. It happens to be 0 degrees latitude, but it is a line of latitude. And the prime meridian that runs through Greenwich, England, is the prime meridian, or a line of longitude. The opposite side of the globe from the prime meridian is the international date line in the middle of the Pacific Ocean. So here is the obligatory tourist shot of someone straddling the prime meridian, and I do have to confess I have done this. I do have a photo of me straddling the prime meridian at the Royal Observatory in Greenwich. Here is a monument in Brazil that marks the equator. So if you're ever in Brazil, go and find that. So to measure that, to measure latitude and longitude, latitude is measured north or south, and longitude is measured east and west. Also, if you measure west, those numbers are negative. Okay, so a measure of longitude can be from 0 to 180, or from 0 to negative 180, depending on what direction you're going around the globe. Lines of latitude are measured north and south. So this example here shows Pittsburgh at 40 degrees north and minus 80 or 80 degrees west. Salt Lake City is about 40 degrees north and approximately 112 degrees west of Greenwich. So you'll see it. You'll see latitude and longitude. Sometimes will be defined as degrees, minutes, and seconds. 40 degrees, 26 minutes, 2 seconds north by minus 80 degrees, 0 minutes, 58 seconds. The conversion to that is there's 60 minutes in a degree and 60 seconds in a minute, or 360 seconds in 1 degree. So you can convert those numbers after the degrees into a decimal of the degrees by dividing the minutes by 60 and the seconds by 3600, then adding that together. So you see 40 degrees 26 minutes 2 seconds is actually 40.434 degrees. How does that translate to distance? Lines of latitude are spaced equally. Lines of longitude converge at the poles. So the closer to the pole you get, the smaller the distance between those lines of longitude. So to add that up, we have the circumference of the Earth through the poles, 24,859.82 miles. So you can see the calculation there on how to arrive at that So the Earth actually is not a true sphere. The correct mathematical term is spheroid because it is slightly flattened at the poles due to its rotation. So the length around the equator is a few miles longer than the circumference through the poles. So how do we tell what coordinate system we're using? A lot of that is dependent on the data source, but you can see that red arrow down there in the bottom right hand corner in your map view. When you add data into ArcMap, if it has a projection system defined, you can see down there in the bottom right hand corner that the units here are in decimal degrees. So that is an indication that this is a latitude longitude projected file. You can also right click on the layer in the table of contents and go to properties, and one of the tabs is coordinate system. It will show in there what coordinate system it's using. So there are other types of coordinate systems. There is what's called Universal Transverse Mercator, or UTM. Data that we get from the state of Utah is by default in a UTM coordinate projection. If you get data from local governments, typically they will be in state plane coordinate systems, which are those are specific projection systems for that area of the state. We'll talk about that in just a second. So UTM is a rectangular grid. It covers almost to the poles. There are 60 different zones. Each of them are 6 degrees wide, and depending on where your data lies on the globe will determine which zone you're in. In Utah, we're in 12 North, so just good FYI. State plane coordinates, these were established by the Geodetic Survey back in the 30s for surveying. They can be in feet or meters. And, the local governments use them because they tend to be more accurate on a large scale map. Remember, large scale map shows small area, detailed. It's more accurate at that scale. So there are 125 of these in the United States. There's at least one in each state. Just remember that you can't join them up, so you'll have to make a determination what coordinate system you're going to use. In northern Utah, Utah has 3 zones, as you can see, that run roughly east-west. You have Utah North, Utah Central, Utah South. Salt Lake County is in the central zone. North of Salt Lake County is in the north zone. So it does make for some challenges. If you're using data on a regional scale, you might want to convert them to the UTM coordinate system just for ease in maintaining that correct projection. So here again, you right click on the layer in the table of contents and open the properties tab, the properties window. Go to the coordinate system tab. It will show you which projection it's in, which state plane zone it's in, as well as the coordinate system and the units. Typically state plane is in feet, but can also be in meters. So depending on the data that you get from or where you get your data, will determine the coordinate system. So the Census Bureau always uses GCS, or latitude longitude. Like we said, local governments tend to use the state plane system. Other data providers may use the UTM coordinate system. So check with the data provider, check with the data source, and that will help determine how you deal with it. When you add data to your map, the first layer that you add will set the coordinate system for the data frame. and so long as all of the data layers that you're adding have a coordinate system assigned, ArcMap will convert those on the fly so that everything overlays correctly. This is a huge leap forward when time was you had to manually set the coordinate system on each layer to make sure it was the same. Now it will do it on the fly as it draws. So here's an example again of Pittsburgh. The sidewalks were added first since they were a local data product in the state plane. That set the data frame as a state plane coordinate system, and then throw the census blocks in there, block groups. Since that data layer had a projection system already assigned to it, the software was able to make that conversion on the fly, and everything lines up just nice. All right, let's talk a little bit about map projections. This is the way to represent a curved surface on a flat map. Curved surface of the Earth on a flat map. That's always the challenge, because you always have to give up something, okay, either size or distance or true shape. Think of this as, in my face-to-face class, this is the lecture. I always bring a bag of oranges and have everybody peel their orange in as big a piece as they can and try and show that and press it flat on a map to show just how difficult it is to show a curved surface with a true representation on a flat map. Okay, and there are literally hundreds of different projections that can be used, and depending on how you're going to use your map, the scale of the map. If you have a large scale map, again, large scale, small area, it might not matter if there's a little bit of error in the drawing. But if you're showing a nationwide map, and depending on the distance in that map to, say, calculate the load of fuel for an airliner, you want to make sure you have the correct distance in there. So the easiest way to show this is there are three basic families of projections. There's planar, which is a flat surface, a cylindrical, which is, as it says or implies, a cylinder, and conic, which is a variation on the cylindrical theme, but using a cone to make the projection. So think of the globe as a lamp with a light in the middle of it. As you project that light out, those features on the surface are then transferred to the surface that you're making the projection on. So your flat plane, your cylinder, or your cone, and depending on where you are on the globe, on the surface of the Earth, and how the globe is oriented to the surface, will determine how your projection comes out. Okay, so this is an example of a cylindrical projection called a cylinder, or a conformal projection, and you can see that the size of the features near the poles are exaggerated. If you look at a globe, you will see that Greenland is not the same size as Africa. Okay, but because it is nearer to the pole than Africa, its size is exaggerated. Okay, so everything is at right angles. The shape is preserved, but the scale is distorted. Okay, it is what it is. Okay, an equivalent projection. This is an example of a conic projection. It works really well for mid-latitudes, either north or south of the equator. It preserves accurate area, but scale and shape are a little bit off. So you can come up with a compromise projection here of so you don't get the exaggerated size at the poles. You do get a little bit of a better shape, a little curvature, but it doesn't preserve everything, but it just looks right. You look at it and you think, oh yeah, that looks good. So here's that example I was talking about. Okay, on the left we have a Mercator projection. Okay, this is how a latitude-longitude map of the United States looks. If you're looking at data of the United States and the northern boundary is straight line east-west, you know you're in a latitude-longitude projection. Okay, on the right is an equal area conic projection. So the distance between Los Angeles and New York, which I apologize are in the wrong place. I need to move those lines. On the Mercator projection is a little over 3,100 miles. In the equal area projection, it's 2,400 miles. Okay, it's actually 2,450. So the equal area is pretty close. But if you were calculating a fuel load for an airliner from Los Angeles to New York, you'd want to make sure that you knew it was 2,451 miles. So when is it not important? Again, like I said, if you're using a large-scale map, error is negligible. It's hardly even measurable at this scale, and it really does. I'm not going to say it doesn't matter, but it's not a fatal flaw in your map if you're in the wrong projection. So let's talk a little bit about getting geographic files from the census, because this is going to be part of your assignment. Remember I told you that the geography people at the census and the data people at the census need to go out to lunch a little more often. I'm going to talk a little bit about the geography side of the shop today. And what are called TIGER files. It's an acronym, Topologically Integrated Geographic Encoding and Referencing Files. Okay, TIGER. This is a data product that the census puts together for the decennial census. So all of the geography for the census data, as well as all of the line work that are valid boundaries for those geographies are shown. So you have a really good road layer, really complete road and street layer, railroads, water features, political boundaries, so things like that. So here the hierarchy is goes from the state to the county. Then at the county it diverges, so you can get places in the county. You can also start going below the county level to tracts, block groups, and the smallest geography is the block. Think of it as a neighborhood size piece of geography. Now, as you get to the smaller geographies, to preserve confidentiality and privacy, the data items that are available become more and more restricted the smaller the geography. So depending on what you're looking for, it may not be available at, say, the block level. It may only be available at the block group or at the tract level. So census tracts are kind of the major geography that the census uses. They're homogeneous, roughly the same size of population, right around 4,000 is what they aim for. They're redrawn after or before every census, so that each decennial census has excuse me, has a new set of geography, but those redraws preserve the outside boundaries from the previous census, so that you can aggregate to compare from census to census. The boundaries normally follow visible features, but sometimes they'll follow political boundaries and other invisible features, but mostly they follow visible features. So here's an example of the tracts from the state of Pennsylvania for the 2010 census, which is the most recent. So just looking at this, you can see where the population density is. You can see Pittsburgh there on the left, Philadelphia on the right. Out in the rural areas, those tracts are pretty big to get 4,000 people in them. So here is Allegheny County. This is where Pittsburgh is, showing the comparison between the tracks in 2000 in heavy lines and 2010 in the lighter lines. You can see where they were split for the 2010 census. The dark lines do preserve the outer boundary, and the lighter lines show where the inner boundaries are for the 2010 census. So again, you can see the same thing for the city of Pittsburgh with those tracks and where they were split. So block groups are subdivisions of tracts, about 400 housing units in each, and these do follow visible features. So and then the smallest boundary, smallest geography, is the census block. They're very small, very fine grain, and but again, it's only the basic data that is available at the block level. Okay, so that wraps up Chapter 5. You're going to get practice with census data, but again, keep in mind the coordinate systems and projections that we've talked about. So go through the tutorials again, and until you're comfortable with the process, and then the assignment is 5-1. This is comparing heating fuel by type. It's very similar to the project that we did for Chapter 4, except in this case you're actually going to go and download your own data from the Census Bureau and manipulate your own tables rather than tables provided for you. I will warn you, this will be the most frustrating assignment we have this quarter, and so contact me if you have issues, if you run into problems, or if you get stuck. Remember the issue with making sure the field types in the data table and the attribute table match, so that you can make your join. Okay, so contact me if you have issues, and we'll see you in Chapter 6.